All right, so let's come over to the Cuisenaire rods. And if we're doing that same uh, that same expression was 4/7 plus 2/3. So let's write that here so we know. So 4/7 plus 2/3. And I want you to think about this same exact reasoning. How can I show one whole that can show both of these denominators? And just like with the set model, you can think about 7 times 3. What do you want to create an array, a 7 by 3 array in the set model? Well, we're going to do the same thing with our rods. And so and if you remember, the 7th only had 3 dots in it. So if my 7th then is going to be length 3. 1, 2, 3, 4, 5, 6, 7, right? It's length 3 because there's 7 of them. Then our length 7 is going to be a third. And that's really, really, really important to remember, right? This is just like the commutative property. They're the same length. And this is why this multiplicative reasoning is so important. It's not just a procedure of multiply 7 times 3 and get a common denominator, make equivalent fractions and add. It's about understanding these relationships, right? We can cut this same piece, this same length, or that same, rectangle into 3 equal pieces and into 7 equal pieces. And that's what's important. So now we can call, just like what we did before, define your unit fractions. This is a third, this is a 7th. So let's label those, right? 1/3, there's 3 of them. There's 7 of these, so these are 1/7. And now all of the thinking is done for us. How many 7ths do we want? 4. So we do it 1, 2, 3, 4. How many thirds do we want? 2. 1, 2. And sorry, that's not going to fit, but now we can count all of the pieces. And, or, turn on the numbers and add them. 3, 6, 9, 12, right? 12 21sts is the same as, so again, this procedure of, well, 4/7 is the same as, right? Times 3 times 3, 12 21sts. And 2/3 is the same as, and maybe this is where we'd want to do this, right? This is the length model. So you would really want them all in one line. We don't have the space in this. And that's again why we would want to use the real ones. But 2/3 we know is the same as, right? 7 plus 7, 14 21sts. And so just like with the set model, you can add the 12 and the 14 or just, count them all up. And this is then our 26 21st. And of course, this only has 25 across, so that's why it doesn't fit. Or maybe we want to rearrange these so we have, we can show it, maybe if we can, I don't know if we can show exactly one whole, because that's 14 and that would be 20. We can switch out, right? This one, because again, we're doing length. So there's one whole, see how it's the same length. And then, so we're going to get rid of that guy. We have this, and then 2 more. Or maybe it would make more sense if I did this, right? We traded out one green one, right? Length 3 for these 3 little white ones. So now we can see one whole and 1, 2, 3, 4, 5, right? You can even do length 5 if you'd like, yellow, or just count them across. So same exact idea, 4/7 plus 2/3. You didn't need to find common denominators first and do that equivalence. What you needed to do was reason about the size of the whole, define each of your unit fractions, and then boom, add them, right? And then in our case, we saw it was 26 21st, or we could rearrange this to be 1 and 5 21st. Either way works.